Welcome to House of Past Paper Solutions. This is the 9709 Mechanics May June 2016 paper 4-2. Alright, let's get going. Not only will I be showing you how to solve the questions, but I'm also going to explain a couple of the concepts that you can take away from this video. So please stick around to the end. Question 1 reads, coplanar forces of magnitude 7 newtons, 6 newtons, and 8 newtons act at a point in the directions shown in the diagram. Given that sine alpha is equal to 3 over 5, find the magnitude and direction of the resultant of the three forces. Alright, so we have a point and then we have three forces acting on that point. So to get the resultant, which means the overall force, the impact, the overall effect of all these three forces at that point, that's what we need. So what we'll do is we need to find the resultant force in the x direction, the component that resulting in the x direction. So it's going to be in the y direction here, the y direction, and then we need that resultant in the x direction. So these are the components. So then the resultant is going to be r, something like that. And then we're going to have theta, the angle at which is going to be acting with relative to the x direction. So the way I'm going to approach this question is then to get the x direction, I'm going to resolve the 8 Newton force, and then I'll get the components, the x and y components. So I'm going to get this component, and then I'm going to get this component here, right? That's what I'm going to do. Same with the 6 Newton force. I get this component and that component, the horizontal and the vertical components for each of these forces. So in the x direction, right? X direction, this is what I'm going to have. I'm going to have x. I'm going to take force is going to the left, going to the right is positive, and then force is going to the left is negative. Remember, force is a vector, and that simply means that it has a magnitude and a direction. As you can see, the forces have arrows, which means they also have their directions in which they act. So in this case, when I'm resolving for these forces, I'm going to take the force going to the right as a positive, and then the force going to the left as the negative, right? And then I'm also going to do the same with respect to the up and downward direction. Upward direction, I'm going to take that as positive, and the downward direction is negative, right? So I'm going to say the resultant x is going to be equal to 7, which is in the positive direction, right? And then I'm going to subtract minus because other forces are acting in the opposite direction, which is to the left. So I have to resolve the 6 Newton force, and I have the angle alpha right there. So this, if I resolve this part here, this is going to be a triangle, and then this is just going to be equal to 6 sine alpha, right? So then I'll write my 6 sine alpha right here. Then I'll have 6 sine alpha. And then I'll also do the same with the 8 Newton force. So it's going to be equal to minus 8. And then how do I get the angle? All right, let me zoom in and show you how I get the angle on this part here. So we know that this whole angle, this whole part is equal to 180 degrees. We know that the sum of that is equal to 90 plus alpha. So to get this angle which we need, which is going to help us to resolve this 8 Newton force in the horizontal direction and in the vertical direction, like that, right? I'm gonna have to say 180 minus 90 plus alpha, like that, and then that is just going to give me 90 minus alpha. So I know that this angle here in green, this angle in green here is going to be equal to 90 minus alpha, like that. 90 minus alpha, and that would ultimately mean that this angle here is going to be equal to alpha, right? So I could either use the 90 minus alpha or just the alpha right there. But to make things simple, I'm just gonna use the alpha, because anyways, if I write here sine 90 minus alpha, right? For this angle, yeah, to resolve in the horizontal direction, like that. This whole thing is just going to simply equal to cos alpha. So I'm just gonna write cos alpha altogether. Cos alpha. And then we'll also resolve, then yeah, then that's it for the x. We've resolved both of our forces for the x direction. Excuse my voice. Then I'm gonna do the same for the y direction as well. Y direction, it's going to be, I'm gonna resolve the forces. So in this case, I'm gonna resolve the 80 Newton force upwards, and it's gonna be y is equal to 8 cos, equal to 8 sine, sorry, 8 sine alpha, and then right, 8 sine alpha, and then I'm gonna resolve the 6 Newton force here, 6 cos alpha, like that, right? And then I also know that sine alpha is equal to 3 over 5. Whenever you have one trig ratio, that means you have all three trig ratios. So I'm gonna have sine alpha is equal to 3 over 5. If I draw a small triangle to represent those right, so this is just about 90. I know it's not accurate. But we're gonna have, so we know that from SOHCAHTOA for the trig ratios, we know that sine is equal to opposite, which is 3 over hypotenuse, which is 5. If we carry out the Pythagoras theorem, we know that this is 4. But we just know that it's the 3, 4, 5 triangle, right? Therefore, my cos alpha is going to be equal to the adjacent, which is this, the 4, over the hypotenuse, which is a 5. Then I can substitute these values in my equation, right? So I'm gonna have x is equal to 7 minus 6, 3 over 5 minus 8, 4 over 5. Then that means x, this is gonna give me an x of negative 3, right? That's the x value that I'm gonna get, right? Then I'll do the same for the y. Y is equal to 8 3 over 5. We're replacing the sine alpha minus 6. The cos alpha is 4 over 5. So I'm gonna get y is equal to 0 actually, right? Then remember, we say that these are the components of the resultant force. So when you resolve, let's say you have the resultant force, let's just assume it's in that direction, right? Let's assume it's in that direction. This is the horizontal and that's the theta. So if you resolve this resultant force, you're gonna resolve it into the y component, which is 0 in this case, into the x component, which is negative 3. That means it should be in the other direction, right? Like that, negative 3, which means this was an assumption. So ultimately, because there is a 0 in the y direction, ultimately our r here, our r, it's just in the, it's just pointed to the left because we only have the horizontal component of x, which is 3, right? Or we could use the Pythagoras theorem if this is confusing. Use the Pythagoras theorem, we're going to say r is equal to x squared plus the y squared, and then root that, which is just simply going to be equal to root negative 3 squared plus 0 squared. And then you get your r is 3, right? It's just like that. And you get your r is 3, like that. And then the direction is to the left. Remember, the direction that I said, it's a negative 3. It's in the negative direction because the y is a negative 3 like that, and the x is a negative 3 and the y is a positive 0, right? So our r would be in that direction too, right? It's negative, remember, because we designated the direction to the left as a negative. That's how we know it's the left. Remember, the question is saying find the magnitude and the direction of the resultant of the three forces. All right. So our final answer, is going to be equal to R is 3 newtons and it's going to the left. Then you just write to the left like that. And that should earn you your full marks. All right. Second question. Let me just clear this up. So question 2. Let's get on with question 2. It says, the particle P moves in a straight line, starting from a point O. At time t after leaving O, the velocity of P in v meters per second is given by this equation. V is equals to 4t squared minus 8t plus 3t plus 3. All right. So first part, find two values of t at which P is at instantaneous rest. Okay. So when the particle P is at instantaneous rest, we know that V is equal to 0. So we use that fact to find the two values of t. V is equal to 4t squared minus 8t plus 3, right? And then I'm gonna factor these two. I'm gonna multiply that, and then I'll get 12t squared. Get two numbers that add to give you negative 8, and two numbers that multiply to give you 12. That's gonna be negative t2 and negative 60. Then I'm gonna use that. So it's going to be equal to 4t squared minus 8t plus 3 is equal to 0. Then I'm gonna solve the quadratic equation. All right, here 4t squared minus 2t minus 6t plus 3. Here I'm just simply solving the quadratic equation now. Factor the 2t, and you have 2t inside minus 1. Factor the negative 3 out. Factor out the negative 3, you have 2t inside minus 1. All of that is equal to 0. Then this becomes 2t minus 3, 2t minus 1. All of that is equal to 0. Therefore, I get 2t minus 3 is equal to 0. And 2t minus 1 is equal to 0. Thus, t here is 3 over 2 or 1.5. And t here is equal to 0.5. 1 over 2 or 0.5, right? Those are two values of t when the particle P is at instantaneous rest, right? Remember, if you draw the graph, it will look something like this. The graph for the velocity. It will have the intercept right there. It's 3 positive 3. Right, let's just say this is V and this is T. This is what it would look like. And we know that this is going to be 1.5 and this is going to be our 0.5. So these are the values of t at when the velocity is equal to 0. And then this is to be the function for v, right? Vt, this will be the function. Okay, so that's part 1, right? Then part 2 reads, find the distance traveled by p between these two times. All right, so the two times that I got, they were t1 is equal to 0.5 and t2 was equal to 1.5. Those are two times that I have. So to find the distance, we know that the velocity, right? The velocity function that we have, it was as a result, it can also be written as the rate of change of the distance or the displacement with respect to time, right? I'm sure you know this from from calculus, right? And we also know that that same v, the function we got is 4t squared minus 8t plus 3, right? So we can just solve this differential equation, yeah? We can solve that differential equation. And then use the limits since it's saying it's between these two times, which I just were the two times, which is 0.5 and 1.5. So I'm gonna solve for s. So to solve the differential equation, I'm gonna do a separation of variables. Right, so this becomes ds is equal to 4t squared minus 8t plus 3 multiplied by dt, right? And then from there, you can integrate, right? The time limits, I have them t t2 and t1. I have the limits, right? Same for these ones here. Then when I integrate that, I'm gonna get s is equal to 4 over 3 g cubed, right? You add, then you divide. Add 1 to the power, then divide. Then minus 4t squared plus 3t, right? Yes, we can have a constant c, but it's gonna disappear when I use the limits because it's gonna cancel out. It's going to cancel out. Then the limits that I have is 1.5 and 0.5. When I use those limits, plug them in, it's gonna be 4, 3, 1.5. Actually, I'm gonna write 1.5 as 3 over 2 now. Cubed minus 4, 3 over 2, cubed plus 3, 3 over 2. Right, and then plus our c. If you want, you can decide to ignore it. Right. Then this is gonna be subtract minus minus the same thing actually. Minus the same thing, yeah. The only difference is this gonna be half like that plus c, right? When you do that, this whole thing here is gonna give me 0. And this whole thing here is going to give me 2 over 3. Right, so it's gonna be 0 minus 2 over 3. And again I get my s is negative 2 over 3 meters. Remember, it says, the equation says here, find the distance, and our s is the displacement. S usually stands for displacement. And we know that displacement is a vector. It is the magnitude and the direction. The only difference with between the displacement and the distance is the distance doesn't have the direction. So which means we just need the modulus or just the magnitude of the displacement to get the distance, right? So is the magnitude, this is equal to the distance, which is 2 over 3. Magnitude of that is just going to be equal to 2 over 3 meters. And that's our answer. That's the distance right there. Right. That's part 2. Okay, let's move on to the next part. Next question. Question 3. A particle of mass 8 kg is projected with a speed of 0.5 meters per second up a line of greatest slope of a rough inclined plane at an angle alpha to the horizontal, where sine alpha is equal to 5 over 18. So that also means we have tan alpha and cos alpha. Because remember, like I said earlier, whenever you have one trig ratio, that means you're going to get the other trig ratios. You just use a triangle and then you find whatever the missing missing vertices of the triangle is, and then you use the Pythagoras theorem to get that value, right? So the question continues. The motion of the particle is resisted by a constant frictional force of magnitude 15 newtons. So 15 newtons is acting against the motion of the mass. The particle comes to instantaneous rest after traveling a distance x up the inclined plane. Part 1. Express the change in gravitational potential energy of the particle in terms of x. Okay, so for gravitational potential energy, we know that for GPE, we know that GPE, change in GPE is equal to mg, change in height, mgh, right? And our particle is said to be on an inclined plane like that. right? Okay, right. So it travels this distance here up the inclined plane. Travels a distance x in terms of x, right? It says here in the question, the particle travels a distance x up the inclined plane. So this is the x that we have. And we know that this is alpha, right? So to get the height, this change here, this is the delta h, right? Delta h. Uh, that's the delta h. Okay. It's just going to be equal to x sine alpha, right? Using the trig ratios. It's just going to be equal to x sine alpha. Therefore, delta h is equal to x. We know what sine alpha is. It's 5/13, right? Thus, we can answer our question. mg delta h is going to be equal to the mass. Wait, it says express the change in gravitational potential energy of a particle in terms of x, right? Yes. The mass can be 8 kgs multiplied by 10, which is the acceleration due to gravity, 10 meters per second squared, multiplied by x, right? Just multiplied by 5/13. Then when I plug that in the calculator, you get, here's a fraction, 400 over x. You get 400 over x, right? 400 over x, over 13, sorry, over 13x, like that. Or you could write the three significant figures as 30.8x, like that. That's your GPE, change in GPE, right? Okay, great. Use an energy method to find x. So the energy method that we use here is it's like this. Let me show you. You are supposed to know that you're supposed to know that energy in this system is not lost. So energy in is equal to energy out. What is the input energy? It says a particle is projected with speed. So the input energy is kinetic energy, right? Initially it is kinetic energy. Then it loses that kinetic energy as it gains height, right? From above the ground, right? From the ground. And then it also loses some of that energy due to work done on friction, against friction, right? So we're going to use the equation, right? It's mv v squared is equal to change half mv delta v squared, right, is equal to mgh plus the work done, which is force times distance. The distance it will traverse up the plane is x. So this is the work done due to friction. So remember, work is equal to force times distance, and in this case the force is the frictional force. The frictional force is given here, it's 15 newtons. The distance is the x, which it travels up the plane, inclined plane. It travels up the inclined plane, a distance of x meters, right? This is the offer, like that. Okay. The initial velocity we are given, the final velocity, that's when it has stopped, which is 0. So I can write half multiplied by 8 multiplied by 5 squared, right, minus 0 squared, which is equal to 8 multiplied by 10, which is for g, multiplied by the height, which we found is 5/13x, then plus the 15x, right? Then when I solve this side, I'm gonna get 100 this side, and it's equal to, when I remember both of these mgh, and the work done due to friction I've got x, the fx. So I can add them up. I can multiply that and then simplify. That's right. When I do that, I'm gonna get 595 over 13 x, and then the x is just going to be equal to 100 divided by that 595 over 13, like that. When I do that, I'll get my x is 2.18 meters to 3 significant figures, like that. ESF. Okay, and then that's my answer. That's your x. All right, question 4. Question 4 reads, a sprinter runs a race for 400 meters. His total time for running the race is 52 seconds. The diagram shows the velocity time graph for the motion of the sprinter. He starts from rest and accelerates uniformly to a speed of 8.2 meters per second in 6 seconds. The sprinter maintains a speed of 8.2 meters per second for 36 seconds, and he then decelerates uniformly to a speed of v meters per second at the end of the race. The first part reads, first question here says, calculate the distance covered by the sprinter in the first 42 seconds of the race. So we want this distance here. We want this distance at 42 seconds. Okay, we know that distance is given of is distance is the area under a VT graph, right? So we're gonna have number 4, question 4 here, part 1. Distance, which is the magnitude of the displacement, right, on a VT graph, is equal to the area of a VT graph, a velocity time graph, right? In that area, if you look at the shape, look at the shape here. This shape, it's a trapezium, right? So I'm gonna use the formula for area of a trapezium, which is equal to half a plus b h, right? And then it's gonna be half the a that I'm gonna use is this part, 42 seconds, right? All right, 42 seconds plus the b is this part here, the 36 seconds, 42 minus 6, which is the 32 second, which is 36 seconds. Then the height is this, that's the height, which is 8.2, right? And then when I put that in the calculator, I'm gonna get an exact value of 319.8 meters. I wouldn't round it off since in this case it was exact. I didn't round off anything. You plug that in the calculator and then you get this exact value. So I'd rather leave it like that for 4 marks. Then part 2, use an energy, show that V is equal to 7.84. All right, so we know that the distance left at 42 seconds. That's what we're gonna calculate first. This part, we're gonna calculate this distance, right? And then we use our area, the area of this part in blue, the area equation to get the V. Because remember, this is also a trapezium again. Look, if you look at it carefully, there's a trapezium, but then in this case, this would be our A, and this would be our B, and this would be our height, because this is a trapezium again, right? Okay, so the distance left, since we know that after 42 seconds, the sprinter has run 319.8 meters, right? So, but the total distance is 400. So I'm gonna say 400 meters minus 319 meters, 319.8, and I'll get 80.2 meters left, right? Okay. Then I'm going to use the area again, the area equation. The area in this case is equal to 80.2. We also know that that area is equal to half A plus BH, right? So we use that fact. Then we have half. Our A this time around is going to be the 8.2 meters per second. This up to here. That's what the A is going to be. And then the B is going to be the V up to this height here, right? And then the height is just going to be 52 minus 42 seconds. Okay, so it's going to be 8.2 plus V. Then I'm going to multiply that by the 10 seconds, from 42 seconds to 52 seconds, right? Like that. And then all of that is equal to 80.2. When I simplify this side, I'm gonna have so what I'll do is I'll divide by 10 to cancel out this 10 here. Then I'll multiply it by 2, right, to get rid of this half. Right, so I'll have 8.2 plus V is equal to 16.04. Then take the 8.2 to the other side, then V is going to be equal to 16.04 minus 8.2. That will give me an exact value of 7.84 meters per second, and here you have shown that, like that. And that's it for part 2. Now for part 3. Part 3 reads, calculate the deceleration of the sprinter in the last 10 seconds. So I'm just supposed to calculate this slope here. That's the deceleration. Right, so what I'll use is, I'm gonna use the Suva equation. Since as you can see, the deceleration is constant. It's just a straight line with a constant gradient. So I'm gonna use the Suva equation. That's the simplest way to go about it. Right. The Suva equation that I'm gonna use is V is equal to U plus AT. Remember, you can use Suva equations as long as the acceleration is constant. And the final V is 7.84. So I'm gonna final V is 7.84. The initial is this, the 8.2 meters per second, plus the acceleration that we're gonna calculate. In this case, it's gonna be deceleration. It's gonna be a negative acceleration. And the time, 52 minus 42 seconds. Right. Then it's going to be equal to A is equal to 7.84 minus 8.2 over 10, right, seconds. Then you're gonna have a negative acceleration, which corresponds to the deceleration, right? So deceleration is going to be equal to 0.036 meters per second, like that. Okay, that's it for question 4. Now question 5. A block of mass 2.5 kg is placed on a plane which is inclined at an angle 30 degrees to the horizontal. The block is kept in equilibrium by a light string making an angle of 20 degrees above the line of greatest slope. The tension in the string is T newtons, as shown in the diagram. The coefficient of friction between the block and the plane is 1/4. The block is in limiting equilibrium and is about to move up the plane. Okay, so that means that um T, the force is acting downwards and the force is acting upwards, right? It's about to move up. So it's not yet moving, but it's about to move up. Okay, so that means friction is going to act in this direction. Okay, it's about to move up. Find the value of T. Okay, so the first thing that you do when you see this question, the best way to approach this question, guys, is just use intuition, honestly. And then you resolve your forces, and then you can find your values for T, right? Because here, the forces acting up the plane and down the plane are equal, right? The fact that it's in a limiting equilibrium and is about to move up the plane will help you determine the direction, in which the frictional force is acting. Since friction opposes motion, and in this case, the block is about to move up, that means the friction is going to oppose that motion, which means it's going to act downwards, right? So I'm going to draw my diagram, and then I'm going to resolve each and every force whilst you watch. So let me zoom in, and I'm just going to draw right on the diagram so that you see what's going on. Just going to get rid of these. Right. So here we're gonna have one, the weight component. We know that weight acts vertically downwards always, right? So weight acts downwards, and that weight, right? I'm gonna replace it. We have the mass here, 2.5 g. It's gonna be 2.5 g. Remember, weight is equal to the force, right? In this case, force equals to mass times the acceleration, and the acceleration in this case is g. So weight is equal to mg, right? And the mass is 2.5. So it's going to be 2.5 g. Okay. Just in case you might wonder where that came from. Okay. Right. And then I'm going to resolve the t. No, wait. Let me resolve the weight. So the weight acting downwards. In this case, the weight acting downwards. Right. This angle here, if I draw a line, this is going to be 30 degrees. You can prove that geometrically. It's 30 degrees. So this, if you resolve that 2.5 g going in that direction, which is parallel to that direction, is going to be 2.5. So this is the weight acting down the slope, 2.5 g sine theta. Right, so I'm gonna write here 2.5 g sine theta. Right, and then we know that there's also going to be a reaction, which is at 90 direction of the plane, which is going to be at 90, like that. Right, it's actually something like that. It has to be at 90 with the plane, with the reaction. Right, so this means this is like that. Okay, and then we also have, we just know that this is 30 degrees. Just know that this angle is 30 degrees. Then the weight component acting at 90 degrees to the slope, right, is going to be equal to 2.5. You're just resolving it again. Resolving the weight component, 2.5 g cos theta. Right, in this case it's 30. Right, so this should be 30, like that. Okay, and then you also know that you have the frictional force acting down plane as well, since the block is about to move up. So you're also gonna have a frictional force, right? I'm just gonna show it like that. Frictional force, and then just gonna put an F friction force, right? Then I'm going to do the same with the T Newton. So acting up the plane, right? like that. Just resolve that t, which is going to be equal to t cos 20, right? And then the other resolution for the t Newton, which is acting at 90 degrees to the line of greatest slope. For the t Newton, it's just going to be t sine 20, right? So these are the forces that are acting on this particle. So I'm just going to draw a summary of them right here. So that we have a block. So acting up plane, we have t cos. Acting up the plane, we have t cos 20. Down plane, we have 2.5 sine 30, which is the weight component acting down, plus the frictional force, right? And then acting at 90 degrees to the line of greatest slope, we have R, right? Plus T sine 20, the component of the T Newton force, right? Acting at 20 degrees to the line of greatest slope, right? And then acting parallel to the reaction is the component of the weight, the horizontal component of the weight, 2.5 cos 30. Right, so those are the forces that are acting on this diagram. The next thing that I'll do is to use the Newton's second law of motion. Let me show you. So now we move on. Here, we're going to use Newton's second law of motion. I'm going to take this. I'll take this right there. Okay. Next thing we'll do is to use Newton's second law of motion. Right? We know that so from Newton 2, we know that the resultant force. Remember, force is a vector. So this direction, the resultant force is equal to ma, right? It's equal to mass times acceleration, right? And we know that it is equal to 0 because it's still, the block is just in limiting equilibrium, which means it's about to move up. Remember, the question specifies, it doesn't say it's moving yet, it's about to move up. So that means forces acting in the upward direction are equal to forces acting in the downward direction. Since it's neither moving up or down, forces acting in the upward in that direction and forces acting in this direction, they're also going to be equal as well. All right. So I'm going to use that fact. Okay. So, but we also have to know that the friction is given by the formula mu r, right? And then to get the r in our case, in this case, the resultant reaction is going to be equal to mu, and then our r in this case is going to be equal to 2.5. We're going to have, let me show you. Since those two are equal, we're going to have r plus t sine 20 is equal to 2.5 g, right? Sine 30. I'm supposed to have g on all of these, right? On all of this, it's supposed to have g. Even this. Let me show you. This is supposed to have a g. My bad for that mistake. 2.5 g sine. Then here there's also supposed to be a g like that. Okay. For the weight component acting downslope and the horizontal component of the weight. Okay. So R is going to be equal to 2.5 g sine 30 minus t sine 20. Therefore, the frictional force is going to be equal to the mu, which I got as a cot, multiplied by that 2.5 g sine theta minus t sine 20. Yes, like that. That is what the then the next thing that I'll do is to use the Newton second law now. Now I'm gonna use Newton's second law. Okay. Newton's second law of motion. So forces acting up the plane and forces acting down the plane are equal. Right? They give me a resultant acceleration of 0. So I'm going to say t cos 20 is equal to the frictional force, right? It's going to be equal to 2.5 g sine 30 plus the frictional force, which is this whole thing here, right? Which is going to be equal to this whole thing here, right? Like that. And then now I can solve for the value of t. Right? When I simplify that, I'm gonna take multiply the quarter in, and then I'll take the value which is t to the other side. I'm gonna have t cos 20 plus 0.5 sine 20 is equal to 22.5 g, right? Sine 30 plus 6.25. If I multiply the 10 here, the g, remember g is equal to 10, this whole thing becomes 25. 25 sine 30. Okay. So this is this part here. And then when I multiply the quarter here, so 1/4 multiplied by 2.5 multiplied by 10, I'll get 6.5 sine 30. Right? And then we multiply the quarter to the t, I'm gonna have this t here. Remember it was a minus, so when I take it to the other side, it becomes a positive 0.25 sine 20. Right? Then I can factor out the t this side. Then I'm gonna have cos 20 plus 0.25 sine 20. Then it's going to be equal to this whole thing here. Like that. And then I can finally divide. I'll divide this whole thing here by this part that is inside the t. Like that. When I do that, I'm gonna get my value of t is 17.5 newtons. And that's it for that question. Answer 17.5 newtons. You show all of these steps, and you're gonna get full marks. Okay, if you wanna take a screenshot or something, there you go. I'm gonna clear that up for the next question. Okay. Question 6. A car of mass 1000 kgs is moving on a road against a constant force 1550 newtons. Against a force of 1550 newton resisting the motion, right? So this is the resistance. of the motion. So let me draw a diagram. So the scenario looks something like that. We have a car that is being driving force. There's a driving force, and it is a resistive force of 1550 newtons, right? And it's 1,000 kgs, like that, right? That is what we have. So the first question says, the car, the first part says, the car moves along a straight horizontal road at a constant speed of 40 newtons. Calculate in kilowatts the power developed by the engine of the car. We know that power is equal to the driving force, which is d in this case, multiplied by v, the velocity, right? And to get the driving force, we're going to use Newton's second law again, right? Which says the resultant force is equal to ma. So which means d minus the 1550 newtons that is acting against it is equal to ma. But we know that it's not accelerating, it's equal to 0. So that means that is equal to 0. Therefore, d is going to be equal to 1550. That's how we get our value for d. Now we have d, and we also have the velocity. It's given as 40. So our power is going to be equal to 1550. Right, multiply the velocity, 40. You plug that in the calculator, you're gonna get 62,000 watts. But the question says, calculate the power in kilowatts. So power, final answer is gonna be power is equal to 62 kilowatts. We just divide this by 1,000, and these 3 zeros cancel out. That's all. Then that's it for the first part. Part B, part 1B. Given that this power suddenly decreased by 22 kilowatts, find the instantaneous deceleration of the car. Okay, so this is how I'm gonna approach this second part. We just clear this up. Second part. I'm gonna say power nu is equal to power power nu is equal to power initial minus power lost. Right. So P nu is going to be equal to the initial power 62 kilowatts, then minus the power lost is 22 kilowatts. Right. And then that is going to be equal to 40 kilowatts. So this power nu here, I'm gonna denote it within P naught now. P naught is equal to the new driving force multiplied by the same velocity, right? And then this is going to be equal to 40 kilowatts. Right. So we need to find the new driving force. Okay, so the new driving force is going to be equal to T. We know that the V, it doesn't change its velocity. C going to be equal to 40. So this is going to be 40 by 10 to the 3 for the kilo divided by 40. So it means the new driving force is now 1,000 newtons. As you can see, it's now less than the initial speed that we had. So this means this is now the new scenario that we have. This is 1,000 force, and then we have 1550 force still resisting. It's a constant force, remember. So as you can see now, these forces are not equal. So using our Newton's second law, from Newton's second law of motion, or Newton 2, we're gonna use F is equal to resultant force is F is equal to ma. This is gonna help us calculate the deceleration. Remember, we're taking the forward direction as positive and the negative direction as negative. So again, I'll go and say driving force, which is 1,000 newtons minus 1550, the force that is resisting that motion, then multiplied by, remember the mass is just 1,000 kgs, then multiplied by the acceleration. In this case, it's going to be deceleration. It's going to be a negative acceleration, right? Then I'm going to get A is negative 550 over 1,000, right? The mass is what? It's 11,000. It's 1,100. Okay, like that. 1,100 like that. Okay, that is what the mass of the car was. And I'm gonna get an acceleration of negative 0.5, which corresponds to the deceleration, right? So I negative 0.5 meters per second squared, or you could denote it as deceleration here. Is equal to 0.5 meters per second squared. And that's it for part B. Then the second part, it says the car now travels at a constant speed up a straight road inclined at 8 degrees to the horizontal, with the engine working at 80%, at 80 kilowatts. Assuming the resistance force remains the same, find this constant speed. Okay, so I'm gonna clear up this first. All right, then I'm gonna tackle the second part. So 6 part 2. So this new scenario that we have now looks something like this. It's now going up an inclined plane, right? So we're gonna have that acting in that direction. Since it's gonna be something like that at 8 degrees. Okay, but I just don't want to show these lines because it makes the work tedious. Just know that it's now at 8 degrees. So since it's acting at 8 degrees, we know that we still have our constant resistance force of 1550 newtons. And then we have the weight component now acting downwards. Remember, we just did it in the previous question. Weight component, which is going to be 1100 G sine 8 degrees. Okay, and then we have the driving force again. Driving force acting in that direction, right? And then, so I'm gonna use, since I know the power, right? I want to use Newton's second law to calculate d1. I'm just gonna term it d1 right there, right? We know that the acceleration is 0, so force is equal to ma. Again, acceleration is 0. The question says that it has a constant speed, so that means the acceleration is 0, right? Then I'm gonna treat this direction as the positive and this direction as the negative, right? So d1, since because d1 is going to be minus 1100 G sine 8 degrees plus minus again the 1550 is going to be equal to 0, right? Therefore d1 is going to be equal to that. D1 is going to be equal to that, like that. Okay, then I know that the power is equal to d1v, and this is equal to 80 kilowatts, which is 80 by 10 to the 3, right? So v now is going to be equal to 80. This is my d, this is my d there. So v is going to, I'm gonna have to say 80,000, the power divided by d1 to get the value for v. Like that. Then I'll get my new velocity is 25.966 meters per second. So then when I put it to 3 significant figures, it's going to be 26.0 meters per second. And that's it. That's it for question 6. Now, question 7, final part, final question for this paper. If you have stuck around this long, please leave a like and a subscribe, guys. This is going to help me to continue doing these past papers. And these past papers are relevant no matter what year. We're going to be 10 years from now, 15 years from now. it's still going to work because the concepts don't change. It's just the syllabus that changes here and there, but the concepts are always the same. So question 7 reads, a particle A of mass 1.6 kg rests on a horizontal table and is attached to one end of a light and extensible string. The string passes over a small smooth pulley P fixed at the edge of the table. The other end of the string is attached to a particle B of mass 2.4 kg, which hangs freely below the pulley. The system is released from rest with the string taut and with B at a height of 0.5 meters above the ground, as shown in the diagram. In the subsequent motion, A does not reach P before B reaches the ground. So that means B reaches the ground before A reaches the pulley P, right? And then part 1 says, given that the table is smooth, which means it has no friction. And we also know that the pulley has no friction because here it says smooth pulley, right? Given that the table is smooth, find the time taken by B to reach the ground. Okay. Since here we know that the acceleration is going to be constant, we can employ a Suva equation, right? So we can employ a Suva equation since we know that the acceleration is going to be constant. So the Suva equation that we're going to use, it's going to have time since we want time. What else do we have? Do we have the acceleration? Yes, we do. It's g, right? It's in free fall. Remember, it's going to be in free fall. And then what else do we have? We also have the distance that B travels here. It's given here is 0.5 meters, right? So I'm going to use the super equation. So for question 7 part 1, I'm going to use the super equation, which is this S and which is time. S equals to ut plus half at squared. Actually, forget what I said. I said it was in free fall. That's a mistake. We're going to calculate the acceleration, right, for these two particles. And we know that since B starts at rest, u, the initial velocity, is equal to 0. So we're going to have our equation is S is equal to half at squared, right? We're going to put this to the side. Now we need, since we have S, right, and we need T, we don't know what A is, but we can calculate it. We're going to use Newton's second law again, right? We're going to apply Newton's second law. From Newton's second law, Newton 2, right? I'm going to have two equations. See, you're going to have to break down this the system here. Let me show you. So A is going to be this particle, and the forces that are going to be acting on A, there's going to be tension in this direction, right? And then in that direction, um, there's going to be 0 newtons. Remember, it's on a smooth table, so there's not going to be any friction or any component of A acting against the movement for A, right? And then the particle B, it's gonna have the weight acting on it, right? Which is 2.4 g, right? That's gonna be the weight acting on it. And then acting up, the force acting up is gonna be the tension, right? So I'm gonna use this factor, these facts to calculate the value for A, the acceleration. 2.4 g. Okay, this is B. Right. So we know that from Newton's second law, force goes to ma, right? So for A, this is what I'm gonna have. T minus 0 is equal to 1.6, which is the mass, multiplied by the acceleration, right? Then that's gonna be the first equation. The second equation is gonna be 2.4 g minus t, right, is equal to 2.4 a, right? Then this is gonna be the second equation, like that. And then what you can do, just add those so that the t disappears, and then you're gonna have 2.4 g is equal to 4.0 a plus a is going to be equal to 2.4 g over 4, which is going to be equal to 6. meters per second squared. Put that in the calculator. Right. So now we can now take our equation, which is S, this equation here that we wrote earlier, is equal to half AT squared. So the first thing that you think of when you're answering this question is what do you have and what you don't have. And since the acceleration is constant, the first thing that should come to your mind is I'm probably gonna use SUV somewhere along the line. Right? As I answer the question. So our equation is S equals to half AT squared. Sorry, please excuse my handwriting. AT squared. Right? And then I want T. T is going to be equal to 2S over A square root that. Remember, a square root is usually plus or minus, but we know that time is always a positive real number, right? We know that time is always an element of a positive real number. It can never be less than 0. So we can discard the negative. So in this case, I'm going to substitute in the values that I have. Square root 2 multiplied by the distance traveled by B, which is this here, the 5 meters. That's the distance traveled by B, 0.5 meters. Then divide by the acceleration, which we just found, 6 meters per second squared. Right, then I'll get my time is T is equal to 0.408 seconds. 3 significant figures. Right, 3SF. Like that. Yes, there we go. And then that's how what we do for part A. You can take a screenshot if you want. I'm gonna clear this part for part 2. Okay, part 2 reads, given instead that the table is rough and that the coefficient of friction between A and the table is 3.8, so mu, in this case mu is given as 3 over 8, right? And the total distance traveled by, find the total distance traveled by A. You may assume that A does not reach the pulley. Okay, so how I would answer this question is to use intuition. That's the best way. You gotta think what's happening. But think about it. As B moves down, accelerates down. Remember, we found the acceleration of B. It's gonna have an acceleration. In this case, it's gonna be a much smaller value, since we now have acceleration slowing down A, right? Slowing down A. So this is how I would think about it. As B accelerates downwards, right? After 0.5 meters, right? A is probably somewhere. Let's just say, I'm showing. So this is probably gonna be the 0.5 meters there, right? Up to that distance right there, right? So here it's saying that, remember I told us that A wouldn't have reached the pulley when B gets to the ground. Here it says, in the subsequent motion, A does not reach the pulley before B reaches the ground. So that means B reaches the ground before A is at the pulley. So that means we still have some a distance after 0.5 meters, after A has moved 0.5 meters from its initial position on the table, right? So when B reaches the ground here, that means the tension that was pulling, the T that was pulling this direction, that was pulling A, is going to be equal to 0, right? When B reaches the floor. When B reaches the floor, right? It's going to be 0. So that means A is now going to start decelerating. Remember, it's going to have a frictional force acting against its motion. It's going to decelerate. So it's going to decelerate to a velocity of 0. That's when it's going to stop. So what we're going to do, the first method, there are actually 2 methods. So the first method that I'll do is use the intuition one, where I will calculate the acceleration, the velocity that A has after it has moved 0.5 meters, right? When I've calculated that velocity, then from then on, I'm gonna calculate the deceleration now, since it's gonna have a constant frictional force in the opposite direction. I'm gonna calculate the deceleration of A. Then when I also have the deceleration of A, now I'm gonna calculate the final velocity of A. Then now I can calculate I can calculate the distance traveled by A after it has traveled the initial 0.5 meters and after B has reached the ground. Let me show you if that doesn't make much sense. Okay, so just gonna put that right there. This is how I'm gonna approach this question. So first thing that I'm gonna do, right? One, I want to calculate the velocity of A after it has traveled 0.5 meters, right? So in order to do that, I want to use the equation v squared is equals to u squared plus 2as. Since I have v, since I have u, which is 0, right, this is what I want, and I have s, which is 0.5 meters. So I need to calculate A, right? So to calculate A, I'm going to use Newton's second law, right? So first thing, I'm going to calculate A. Calculate acceleration of A, right? To do so, remember now, I'm going to use that system again. A is now like this. A, it is a tension. And then remember it is R, which is equal to 1.6 G. R is the reaction. Then it's going to have the frictional force, F, which is equals to mu R, right? So to get the frictional force, I have the mu, which is 3 over 8, and the R, which is 1.6 G, right? Great. Then I also still have B. Acting down. Force acting down is 2.4 G. Force acting up is T, right? So I'm going to use these two to calculate what the acceleration is. So I have T. I'm going to use Newton's second law, which is the resultant force is equal to ma, right? So in this case, T minus the friction force, which is 3 over 8 multiplied by 1.6 G, right, is going to give an acceleration of mass times acceleration, right? Then B, 2.4 G minus T is equal to 2.4 A. Then I'm going to add those two. Then I'm going to get 1.8 G this side is equal to 4A. Then ultimately, acceleration is going to be equal to 4.5 meters per second squared. Right, there we go. Now I've calculated the acceleration. Now that I have acceleration, the second part will be to calculate the velocity, final velocity, v final, after the particles have traveled 0.5 meters, right? And the tension is now 0, and T is now equal to 0 newtons, like that. So I'm going to use the equation v squared is equal to u squared plus 2as. Remember the initial equation that I wrote here, this here, one here, that's the one that I'm going to use. Then we want v final, this. So v, we know that u is equal to 0. V final is going to be equal to, I'm going to keep it as v squared, it's going to be equal to 2 multiplied by 4.5 multiplied by 0.5. Right, so v squared is going to be equal to 4.5. As you see later, we're actually going to use v squared instead of just v root 4.5. Then I'm going to leave it like that, exact, like that. Now the third part. Now we are here now. A is now at this point. We know that when it's at this point, it has a velocity of root 4.5, right? So now we need to calculate the deceleration since t is now equal to 0. There's no tension anymore because B has reached the ground. So once B has reached the ground, tension becomes 0, right? So A starts to decelerate. Remember, it's still in motion, but it's now deceleration due to the friction that is opposing that motion. Okay, so this is a scenario that we have now. So we have A moving this direction with the tension is equal to 0 now, newtons, but we still have the frictional force acting in that direction, right? So this frictional force is going to decelerate the motion of A until it has reached a final velocity of 0, right? So I'm gonna calculate that deceleration now. So 3. So now I'm gonna calculate the deceleration of A after B reaches the ground or floor. Sorry, the ground or floor, and tension is equal to 0 now, right? Okay, so I'm gonna use I'm going to use Newton's second law again for A now, just only for A though, since we go to force is equal to ma. And remember, this is the scenario that we have now. Now we have 0 minus ff is equal to the 1.6a, which means 0 minus 3 over 8, 1.6 g is equal to 1.6a, right? And we know that when B reaches the ground, t is equal to 0. Therefore, in this case, our acceleration is going to be equal to a negative acceleration, which is a deceleration, 3.75 meters per second, right? Then the next thing that I'll now do is to calculate our distance now. And then I'm going to use the same Suva equation again. Let me show you. So now we're calculating S, right? We're calculating S2 after T is 0, or after the B has reached the ground, right? Recall, this is the scenario that we have now. So if we go back to the table, right? After it has traveled 0.5 meters, right? Now this particle A now is a V of root 4.5. It is a deceleration of negative 3.75, right? That's the deceleration that it has. So now we can use that fact, and we know that it's going to keep moving until it has a final let me just say 2, until it has, so this becomes u1, right? And then this becomes u2, right? This v here becomes u2 until it has a final v2 of 0. So I can use the v squared is equal to u squared plus 2as. Since I have v2, u2, I have the deceleration, now I need to find the distance, right? Okay, that's what I'm gonna use. Okay, so I calculated, I see v squared is equals to, in this case, it's gonna be v2 squared, so to u2 squared plus 2 a2s. This is gonna be a2 here for the deceleration, right? I know that the v squared here is supposed to be 0. I know that the u squared is supposed to be the v, the final velocity after B reached the ground, and we calculated that here. We calculated it here. It's 4.5. So V squared is just 4.5. I'm just gonna plug in this 4.5 like that. So 0 is equal to 4.5 plus 2 multiplied by the deceleration that we had, which is negative 3.75, right, multiplied by the S2 that we need. Therefore, S2 can be equal to 4.5, negative 4.5, divided by 2, negative 3.75. And then when I do that, I'm gonna get an S2 3/5, which is equal to 0.6 meters, right? So sorry, there was a technical glitch. So this is S2 now to get the total distance from the table. So after B has reached the ground, it moves a further 0.6 meters. And it says here, the question says find the total distance traveled by A. So it's the total distance is going to be equal to 0.5 meters plus 0.6. So total distance equal to 0.5 meters plus 0.6 meters, like that. And that's it. You get your, it's going to be equal to 1.1 meters, and your answer can be equal to 1.1 meters. Okay, so this was the long way to work it out, longer way to work it out. So from calculating A to calculating V, and then calculate the deceleration, then you calculate total distance. Okay, so that's one way you could approach this question. But there's another way as well. Let me show you. You're gonna choose which one you want. Let me show you the second way. This one I think is much faster, even though upon looking at the question for the first time, you may not necessarily come up with that intuition. Okay, so the second method that you could do is use an energy method. So you know that energy is conserved in the system. Energy in is equals to energy out, right? Okay, so the energy in, it's coming from the change in gravitational potential energy. That is what is supplying the energy. Yeah, since there's no push, the system is just said to have been released, GPE, which that GPE turns into the total kinetic energy for both A and B, right? And then some of it goes to the work against friction for the particle A, right? So then you go, the GPE is only coming from particle B, right? From B. So I'm gonna write MB G delta H is equal to the half MA delta V squared plus the half MB delta V squared plus the frictional force, which is just Fs, frictional force multiplied by the distance traveled, which we want, right? So then you can substitute in the values 2.5 multiplied by 10 multiplied by 0.5, the height moved by moved by the particle B is equal to, then you can just write this, you can write this here, this part here, you can just factor out half and the change in velocity squared. So which means it's gonna be half ma plus b. It's gonna be something like this, half ma plus mb delta v squared. Okay, I'm gonna replace that with the actual values of by 1.6 plus 2.4 for the masses of the particles applied by the change in velocity, which is v squared final, right? I want to calculate the final velocity. V squared final, 0 squared, plus the frictional force, which is 3/8, 1.6 g, multiplied by the distance traveled by a. This is the distance traveled by a before, as soon as b reaches the ground, right? So then I can take this to the other side, and then I'm gonna have, and then this here, this whole thing is gonna be 12, and this whole thing is gonna be 3, and then this whole thing here is gonna be 2. So I'm gonna have 12 is equal to 2 v squared plus 3. Therefore, v squared is equal to 12 minus 3 divided by 2, which is just simply 9/2, or 4.5. See, remember, this is the same 4.5 that we got earlier. So this is the velocity squared of a after a distance of 5 meters, after all of the gravitational potential energy, all of the gravitational potential energy that B had, right, has been used up, has been converted to kinetic energy of B and kinetic energy of A, and also there's work done against friction. So after that distance is 0.5 meters, the final velocity for A is going to be equal to 0.45. It's going to be equal to 4.5, right? And then after that, what you want to do now is to calculate the final distance that A travels, and then you're gonna use the energy method again, right? So you're gonna say energy in. Now you're concentrating with A on energy in for A, equal to energy out, right, for A again. So the kinetic energy that A gains, where does it go into? It goes into it is converted into the work done against friction, right? Just for A only. So we want that kinetic energy after. Remember, now it is a velocity of root 4.5, right? And it's gonna be losing energy due to the frictional force. And we know that the work is gonna do from here to the end when v is equal to 0. The final velocity is equal to 0. That's what we want. So the change in kinetic energy is going to be equal to half mv delta v squared, which is equal to the frictional force multiplied by the distance it travels, s2, right? And then you can see half m v squared minus 0 squared, since it's going to be the final velocity, and then the initial velocity is going to be this part here. Okay, it's equal to 3.8. The frictional force, we already found that, which is 1.6 g multiplied by h2. Then you can substitute in those values, half multiplied by 1.6 multiplied by 4.5. V squared is 4.5. Then it's equal to 30/8 multiplied by 1.6 multiplied by h2. Then h2 is going to be equal to If you plug that in the calculator, you're gonna get 4.5. Yeah. You can cancel out this 2 and then multiply by 2 to the other side. You're gonna get 4.5 over 7.5, which is gonna give you 3/5 or 0.6 meters. See, so this is the distance traveled after. This is the distance traveled after particle B has reached the ground. So S2 after B reaches the floor. Okay. So the total distance going to be equal to 0.6 meters plus 0.5 meters initially moved. Then you get your 1.1 meters. See, same answer. So this was the second method which you could use to approach this question. I don't know, you choose which method is best and then you apply it. Anyways, that's it for this paper. Please guys, if you enjoyed this paper, please consider subscribing. Please consider to subscribing. Subscribe, like, share. Please subscribe, like, and share so that I can continue to make these videos a success.